Welcome viewers to the fourth segment of the seventh lecture for the online series of lectures for the course of Algebraic Topology 1. In this segment we are going to study an example 6. Consider the complex M indicated in the figure below. Whose underlying space is a square. Hence is a two-dimensional complex. So let me draw this complex M V0, V1, V2, V3. These are the vertices, and there are these edges which we call E5. This one is called E5, this one is called E6, this one is called E7, and this one is called E8. This edge is called E1, this one is called E2, this one is called E3, and this one is called E4. Okay, and there are two simplices, right? This is sigma 1 oriented counterclockwise. This is sigma 2 also oriented counterclockwise. Then we have sigma 3 oriented counterclockwise, and finally we have sigma 4, which is also oriented counterclockwise. Okay, figure 6, 2D complex M. Now instead of computing the group of 1 cycles, we reason as follows. Okay. We take shortcuts in the following way. Given a one chain C, okay, so we take a generic one chain C on this complex M. Okay, let E be its value on the edge E1. This is the edge E1. Okay, so we know the value it has on the edge E1, right? Given that one chain C. Then we claim that the one chain given by the following expression, C1 is equal to C plus del 2 A times sigma 1, given by equation number 16, has value 0 on the oriented simplex E1, in the oriented one simplex to be more precise, E1. Okay. So let's check by direct computation that this is indeed true. We let us write this generic one chain C as C equal to A times E1 plus sum of all these expressions Ni Ei, where I is not equal to 1 and Ni are integers. Okay, this is equation number 17, right? You see that from this expression 17, it's clear that the value of this one chain on the edge E1 is A. On the oriented one simplex E1 is A. Okay, then 16 immediately reads 16 immediately reads C1 is equal to, so let us plug in 17 in 16 to have AE1 plus sum of all these expressions Ni Ei as I varies, right? But I is not equal to 1. Okay, and so when we compute the boundary of this two chain sigma 1, we get plus A times E5 plus E2 minus E1, right? So we have AE1 plus sum over all i's except for 1, NiEi plus AE5 plus AE2 minus AE1, and this minus AE1 cancels out against AE1. Okay, so we can write it as sum of all Ni prime Ei, where I is not equal to 1, for some Ni prime in the set of integers. Okay, this is equation number 18. Okay, so since in this summation there is no so I is not equal to 1, which means that the value of C1 on E1 is 0. The value of C1 on E1 is 0. Okay. So how does one interpret 16? One interprets 16 as the fact that after modifying the one chain C by adding a boundary component, by adding a boundary to C, one pushes it off the edge E1. Okay, so first of all, when we took this elementary one chain C, it had a non-zero value on this edge, right? So what we do is that we take that one chain C and add a boundary term to it to modify it by adding that boundary component to obtain a new one chain, and the value of that new one chain is going to be 0 on this edge E1, which means that we are pushing this this one chain C of E1 by adding this boundary term. Okay, so this is what one says. So let me erase this spot. I need to keep the figure. One says that one pushes C of E1 by adding a boundary term to it. Okay, so push C of E1. Okay, I put it inside quotation. It's not a regular term. So by pushing, so we already explained what it means by pushing on one chain of an edge. Okay, all right. The next goal is, so we have a new one chain which is C1 that one obtains from C by modifying C by a boundary component. Okay, now the next goal is to work with this new one chain and push it off this edge E2. Next goal is to push C1 off the edge E2. Okay, let B be the value of C1 on this edge E2, that is, so let us write C1 is equal to B times C2. That means that the value of C1 on this oriented one simplex E2 is B, plus sum of all the expressions Ni, Ei, where I is not equal to 2. Okay, because I extracted out the E2 part here, so there is no E2 part here, and where Ni's are all integers. This is equation number 18. Now we define a new one chain C2 by adding a boundary term to C1, which is del 2 of B sigma 2. This is equation number 19. Okay, now this, so after plugging in the value of C1 from 18 into 19, this is BE2 plus sum of all the terms Ni, Ei, where I is not equal to 2, plus, now this is B times delta 2 sigma 2 is going to be, you take the boundary of this 2 chain, and this is going to be E6 plus E3 minus E2, right? So this BE2 cancels against this BE2 minus BE2, so that we have so there is no, so I is not equal to 2 in this expression, and we can write it as Ni prime Ei for some Ni prime in the set of integers. Okay, we can do that, and this we number this equation by 20, and 20 tells us that tells us that the value of C2 on on this edge E2 is 0, right? Because there is I is not equal to 2 in this expression 20. So that we indeed pushed C1 off E2. We indeed pushed C1 off E2. Okay, so now we have a new one chain C2, right? So the next goal is to push C2 off this edge E3. Okay, let me erase this part. Push C2 off E3. Okay, so for that we modify C2 by adding the following boundary term d sigma 3, okay, which is equation number 21. Okay, now write where you see that it's so where did we take d from? We started with C2. So in the previous step we ended up with this new one chain C2, which the value of which on the edge E2 was 0, right? Now so we suppose that C2 has a non-zero value on the edge E3, and that is P. Let and that is G, sorry. Let D be the value of the two chain that we obtained in the previous step, the value of C2 on E3. So now the claim is that if I write C3 as C3 as C2 plus del 2 times D times sigma 3, then for this chain C3, so the value of C3 on E3 will be 0. That's the claim. Let's see how it works. Write C2 is the one chain that we found earlier. Okay, C2 is the value of it on E3 is D, right? So we write it as D times E3 plus sum of Ni EI, where I is not equal to 3 because we extracted out the E3 part from this sum, and we want each of these coefficients to be integer, right? That's equation number 22. Equation number 22. Now from 21 one obtains C3 is equal to DE3 plus sum of all the terms NIEI, where I is not equal to 3. This is C2, and then D times, then the boundary of sigma 3 is E7 plus E4, E7 plus E4 minus E3, right? So dE3 cancels against this minus dE3, so that we have some Ni prime times Ei, where I is not equal to 3, and these Ni primes are some integers. So this is our equation number 23. So equation 22 reveals the fact that indeed the value of C3 on E3 is 0. The value of C3 on E3 is 0. In other words, we have been successfully able to push C2 off E3 by adding a boundary term. Okay, good. So using 16, 19, and 21, using 16, 19, and 21. Okay, so let me write those, I need to write those equations so that you understand clearly what's happening. So let me write 16 again. What was 16? 16 was C1 is the modification of the given one chain in the first step. C1 was equal to C plus the boundary term del 2 A sigma 1, that was 16. And what was 17? 17 was a modification in the second step. It was, no, it's we don't want 17, we want 19, right? So 19 is given by C2 is equal to C1 plus delta 2 B sigma 2. This was 19. And what's 21? Let me write 21 for you. 21 is the modification in the last step or the third step, C2 plus del 2 D sigma 3. This is 21. Okay. So now from which it follows that C3 is equal to C plus del 2 A sigma 1 plus B sigma 2 plus D sigma 3. This is equation number 24. So from 24, one concludes that given one chain C, one can find a chain C3 that is homologous to C, homologous to C, and carried by the following subcomplex, or by the subcomplex drawn in the following figure, drawn below. So we get that subcomplex from the complex M by excluding these three edges, right? E1, E2, and E3, right? Because by appropriate modifications to one chains, we have been able to push the one chain of these three edges, and that is the reason the one chain is only carried by a subcomplex, which one obtains by excluding these three edges. So let me draw that subcomplex for you. This is the subcomplex. So I need to put this figure somewhere, which I will not erase for a while. Okay. So let me draw it here. V0, V1, V2, V3, and at the center this vertex V is here, and this edge is also here. So E5 is here, and this is E6, this is E7, and this is E8, right? And this was E4. So we just excluded E1, E2, and E3. So this is the subcomplex. So we found that the chain that we started with, the one chain that we started with, is homologous to a one chain carried by the subcomplex of the given complex M. Okay. Now, in addition, if the one chain C happens to be a cycle, then C3 is also a cycle, right? Okay, so if the one chain C that one starts with is a cycle, C3 is going to be a cycle as well, because C3 is homologous. We have shown that C3 is homologous to C. Okay, so let C3 is equal to, so we know that C3 is carried by the subcomplex. So C3 is equal to N8 E8 plus N5 E5 plus N6 E6 plus N7 E7 plus N4 E4. Okay, this is equation number 25. This expression tells us that the value of this modified one chain C3 on the edge E8 is N8, on the edge E5 is N5, on the edge E6 is N6, on the edge E7 is N7, and on the edge E4 is N4. The value of C3 on the three edges E1, E2, and E3 were all 0. Okay, right. So that the boundary, so the boundary operator acting on this one chain C3 is going to be equal to N8 times V0 minus V3, right? V0 minus V3 plus N5 times V1 minus V0 plus N6 times V2 minus V1 plus N7 times V3 minus V2 plus N4 times V minus V3. Okay, and it can be written down in the following way: N8 minus N5 times V0 plus N5 minus N6 times V1 plus N6 minus N7 times V2 plus N7 minus N8 minus N4 times V3 plus N4 times V. Okay, So the only way this guy can become 0 is to choose n4 equal to 0 and n5 equal to n6 equal to n7 is equal to n8. So this is the case. So C3 will also be a cycle if this condition holds. Okay. So we thus find that for the one chain C3 to be a cycle, it must vanish on the edge E4. On the edge E4. Okay. All right. So it means that um, every one cycle of the complex M is carried, or so it's better to write it this way: every one cycle of the complex M is homologous to a one cycle that is carried by the boundary of the square. One cycle carried by the boundary of the square. By the boundary of the square. Okay. So initially, what we saw that the one chain C3 is carried by this subcomplex. We then put the additional constraint that this one chain is also one cycle, and then we saw that it also vanishes on this edge E4, from which we conclude that any one cycle on this complex M is homologous to a one cycle that is carried by the boundary of the square. Okay, that's only non-zero on these four edges. Okay, good. By plugging in n5 is equal to n6 equal to n7 is equal to n8 in equation 25. Let me write it for you again. So let me write equation 25, which was the generic expression of this, of this one chain, n8 e8 plus n5 e5 plus n6 e6 plus n7 e7 plus n4 e4. Okay, this goes away, right? When we take C3 to be a one cycle, then this goes away. Since we are just dealing with one cycle now, this immediately goes away, and all these coefficients are the same: n8, n5, n6, and n7. So one finds that this C3, so the expression of this one cycle is n5 times e5 plus e6 plus e7 plus e8. That is such as one cycle must be, that is such a one cycle must be an integral multiple of e5 plus e6 plus e7 plus e8. Okay, this is one result. One also verifies that the boundary of this two chain sigma 1, the boundary of the two chain sigma 2, so the boundary of the two chain sigma 3 and the boundary of the two chain sigma 4, the sum of the boundary of all these two chains is equal to e5 plus e2 minus e1 plus e6 plus e3 minus e2 plus e7 plus e4 minus e3 plus e8 plus e1 minus e4. So that e5 cancels against that, e5 stays. e2 cancels against this e2. e1 is cancelled against this e1. e6 stays. e3 is cancelled against this e3. e4 is also cancelled against this e4, so that we have e5 plus e6 plus e7 plus e8. Okay, which tells us that C3 so we found earlier that C3 is this guy, right? So which tells us that C3 is equal to N5 times del 2 sigma 1 plus del 2 sigma 2 plus del 2 sigma 3 plus del 2 sigma 4, right? Which is nothing but del 2 of n5 sigma 1 plus n5 sigma 2 plus n5 sigma 3 plus n5 sigma 4 for some n5 in the set of integers. Okay, so this is the final expression of C3 being a one cycle. Therefore, so we don't need these figures anymore. Therefore, this one cycle C3 is homologous to 0, we have seen, or C3 simply bounds. Okay, because so C3 can be written as a boundary term, therefore C3 is homologous to 0, or C3 bounds. Since the given one cycle, since the given one cycle is homologous to C3, the one cycle C also bounds, right? Whatever happens with C3 will also happen with C, because C3 is homologous to C. So C also, the one cycle C also bounds. We thus find that every one cycle of the complex M bounds, and hence the first homology group of M is trivial. Okay, let me erase this part now. Now the higher dimensional homology groups are generic two-chain on the complex M. Get back to the figure of the complex and see that there are 4 two-chains, right, in the complex. So a generic two-chain on the complex M is given by C is equal to M1 sigma 1 plus M2 sigma 2 plus M3 sigma 3 plus M4 sigma 4. This is equation number 26. Okay. If C is a two-cycle, then one should have delta 2C, which is a one chain, right? This is going to be equal to M1. So, so let me draw the figure again. So the complex M, V0, V1, V2, V3, and let me draw the edges. This is E1, E2, E3, E4, and this is E5, E6, E7, and E8. Okay, and there is sigma 1, sigma 2, sigma 3, and sigma 4. Sigma 1 is this with the counterclockwise orientation, so is sigma 2 and sigma 3 as well, oriented counterclockwise. All the 2 simplices are oriented counterclockwise. Okay, so this was the picture, right? So from this one sees that this one chain, the boundary of the two chain C is given by M1 times E5 plus E2 minus E1, okay, plus M2 times E6 plus E3 minus E2 plus M3 times E7 plus E4 minus E3 plus M4 times E8 plus E1 minus E4. Okay, and do some manipulations to find it as M4 minus M1 times E1 plus M1 minus M2 times E2 plus M2 minus M3 times E3 plus M3 minus M4 times E4, then plus M1 times E5 plus M2 times E6 plus M3 times E7 plus M4 times E8. Okay, So delta 2 of C is equal to 0 if and only if M1 is equal to M2 is equal to M3 is equal to M4 is equal to 0. Okay, it means that, so this tells us that the group of two cycles on the complex M is trivial, which leads to the fact that the second homology group for the simplicial complex M is also trivial. Okay, all right. So now there are a few important things that we need to say at this stage. The underlying spaces for the complex L and M for this example and L from the previous example, right? In both cases, the underlying spaces are the same, which is a square, right? Using the results of the respective examples, one also finds that the homology groups are the same in the two cases, which is expected, right? This validates the fact to be proved in the second course of algebraic topology too, that the homology groups of a complex depend only on the underlying space. Okay, so the underlying space in both the cases was square. Okay, so that's pretty much it. This is what I wanted to do in this seventh lecture, basic computations on homology groups for simplicial complexes. This is what we call simplicial homology. Okay, so there are further results on simplicial homology that we'll cover in the second part of this course. Okay, so at this stage I give you some exercises from the book by Moncrief, suggested exercises, elements of algebraic topology, by Moncrief. Okay, section 5, problem number 1, 2, 3, and 4. Work out these problems and they will be helpful. Okay, thank you for attending the seventh lecture.